As a background to the module on distribution systems, we need to understand that when we initially generated electricity, it was done so by the means of direct current generation. And the voltages at that time were very low because it was the first thing that was done and it was the easiest way that they could be able to manage the generation. Then, as the years progressed and the need for electricity rose, we then invented the transformers. And with the transformers, then came the alternating current. And so, therefore, what we're going to talk about in this chapter is to discuss both the DC as well as the AC distribution systems that we have. So our direct current is really a flow of electricity in only one direction, and it can be seen or represented with the diagrams that you see at the bottom, where you've got on your flow chart that it just shows it's a straight line going across. It doesn't go up or down in magnitude, it stays at that same value. And then you can see on your circuit diagram that there's the DC source with the plus and minus sign, and it's represented by a battery because batteries are DCs. And then you can see the load, and it moves from the negative side, going through the load all the way back to your source again. While on your AC, you have your current flowing in what we call a periodic direction. So therefore, your sinusoidal wave, as you can see now at the bottom left-hand side, will move from a 0 point going up, and then it goes all the way down again to the 0 point, and then it goes below that point. So that's why we say it changes direction periodically. So every 180 degrees, you've got a change of direction that is going to be happening on your AC source. And your voltage in your AC circuits are also defined as periodically, and they reverse because your current is changing direction. So when you see here then on your circuit diagram for it, there is your AC source, and you can see that the current here can go either way. It can go away from the source or it can go towards the source going onto your load side. So it basically means that you can have a scenario here where if one of your two lines from your source going towards your load were to have a problem and it became open circuited or it blew or whatever the case that the problem might be, you could still be able to get supply to your load by supplying it on the other side from that AC source. Whereas on your DC, if you lose that negative line, then that's it. You don't have supply that's going towards your load. So the major differences then between your direct and your alternating current are as follows. Firstly, in DC, as we stated already, your current only flows in one direction compared to your AC that it changes direction periodically. On your DC, you are unable to transfer power over long distances as you've got very large energy losses or rather resistance losses that you get on your line. For your AC, you are able to travel over long distances, and this is with the help of the transformers, as they are able to transform into certain voltages for you to be able to do the traveling with very minimal losses on your line. Then you've got what we call the frequency. So on DC, there's no frequency, it's a zero. Compared to in AC in South Africa, we are sitting at a 50 hertz frequency, and in other countries, they sit at 60 hertz frequency. Then the current of your magnitude vary with time constant on your DC, whereas on your AC, that magnitude only varies with time. We have got a source, which could be a battery or a cell on your DC, And on your AC, that could be a generator, or it could be your mains, in other words, your switchboard as you come through into your houses. Then in DC also, we've only got resistance on your lines, whereas your AC have got resistance with capacitance and inductance. And that is why when we talk about lines, we usually talk about impedance. We're referring to AC lines where you've got resistance, inductance, as well as capacitance in it. You only have a power factor that is always a 1 on your DC, while on your AC, your power factor could be anything between 0 up until 1. Then your waveform are pure and pulsating on your DC. So they're just an on, off, compared to your AC, where you can have a signal, or it could be a triangular or a square that you have. So as we sit now, for the transmission of power, we are utilizing your AC systems. And then your DC, we usually use it to drive machinery such as your variable speed drives, such as electromechanical projects, and it also gets used on trains, what we call the electrical traction lines. So it's those lines that you see just above some of these electrical trains, that is your DC supply. Then for our transmission, we usually go from your generation where the power is being done either at a power station of coal or nuclear or any other form of a power station that is there, and it travels and goes to our load centers. And the primary purpose of our distribution systems then is for us to be able to cater for the customers' demands of what energy they require in order to supply all of their appliances at their end. And after they receive this bulk electrical energy from transmission, we are then able to deliver it to the customers. So that is what the distribution system does in essence. And there are two major types of distribution substations. And your substation, you must remember, it is where your voltages are either being put up, stepped up, or they are being stepped down. So for distribution, we usually are going to step down our voltages into voltages that can be accepted by the customers. So we've got primary substations, and those would usually be your ESCOM typical substation, or it could be a BCM or any other municipality that has got a license to be able to supply electricity to people. Then you've got your customer substation. So institutions like WUSU or institutions like Forte and all of those other major customers usually also have substations where they receive the electricity from whoever our supplier is. So we call those customer substations. So voltages that you find in our distribution systems are anything from your 220 volts that we have in our mains in our houses all the way to 132 kV. So our medium voltage, which is where the distribution system really exists, is anything between 2.4 kV up to 132 kV. So that medium voltage is divided into two sections. The first part being the 2.4 to 33 kV, and that is for relatively small to medium distance lines. In other words, the distances there are never above 100 kilometers. And then for your longer lines, we're going to have voltages of distribution between 66 kV and 132. And those systems in distribution usually consist of distributors, feeders as well as what we call service mains. So your distributors are really what is designed to be able to tap your voltages in order for you to give the customer the voltage level that they are requiring at their point of supply. Then for your feeders, we're talking about conductors that are used to connect areas from your substations in order to power your network, and they are used for your current carrying capacity. And so therefore the size of the load to be supplied is really dependent on your feeder. So you need to be able to choose or to have the correct size of your conductor, be it an overhead line or be it an underground cable, because those can limit the amount of supply you can deliver to your customers. Then we've got your service main, and these really connect your distributors to your customer terminals. So in other words, it should be right at the end where you or the supplier stops and the customer starts. So in most cases, if you go around towns and you notice there are these small boxes that would sit outside people's yards, and those would be what we call the service mains, because in there the distributor, be it ESCOM or be it a municipality, that's where they end. And then the customer has to connect their own cable from that side going into their premises. So that's why we talk about the customer terminals. At the same time, if you look into your house, ne, your service mains in your house will be that small prepaid meter, because that meter is where the distributor ends in its point, and it's where your cable as a customer gets connected to in order to go to your main switch box, and then you are able to make sure that you've got your lights and plugs in your house. Then the distribution systems, they get classified according to the nature of current. So are they DC or are they AC? They get also according to your construction. Are they underground or are they overhead? As we said, that's where your feeders are going to be. Then we talk about the connection scheme, and the next slides are going to really discuss the connection scheme. Is it a radial network? Does it just move from your source point to your load? Or is it a ring network? Does it go all the way around? Or is it an interconnected network? You have it going all the way around and then have a single or a specific feeder dedicated to move from the source directly to the one of those feeders that you have. So for you to say you've got a good distribution system, you need to make sure that your system is reliable. Because what people do not want is customers that are paying for that supply. They don't want to be experiencing power outages all the time due to whatever is it faults or is it whatever is the case. They don't want that. So those should be as minimum as possible at all times. And if they happen, they need to be very short. The second point is that your power must be available to your consumers at any quantity that I require. So if I'm wanting a point of supply for a complex and that complex only requires 2 MVA today, and next year I have extended my mall and I wanted to have a 10 MVA, the distributor must be able to give that to me. Then your declared consumer voltage should remain within our prescribed limits. What does the law say? The law says that I should not have a voltage that is less than 5% of the declared system voltage. So when it gets to me, if I'm getting voltage from the supplier that is supposed to be 220 volts, when I measure at my socket, I must not get less than 250 volts in there. Then we talk about efficiency of our lines, and we say that they should at least be 90% efficient. We obviously would love to have a scenario whereby your lines become perfect at 100% efficient, But unfortunately, because we're talking about electricity, because we're talking about conductors, because we're talking about transformers, those can never be really 100% secured or 100% efficient. So therefore, we're wanting it to at least be 90%. Then your transmission lines should never be overloaded, because if you overload your transmission line, you run the risk of having insulation failure in them as time goes by. And if that happens, you run the risk of losing the transmission line. If you lose a transmission line, you lose a lot of customers at distribution level, because remember, your transmission is what connects or what brings the power from generation up to where the customers are at. Then your insulation resistance on your entire system should be pretty high, so that there is no leakage probable danger to any human life. So if you are working in a vicinity where there is electrical lines or where there is a substation, you should never be harmed by the conductors or by the current flowing within those conductors. And we obviously want the system to be economic. So the last two slides dedicated on this presentation of lesson one are going to be looking at your connection schemes. Remember, I mentioned one of the three factors that determine our distribution is the connection scheme. So the first one to look at is what we call the radial distribution system. And what you see in front of you in that picture is that you've got a generator, which is 100 MVA at 33 kV, and then that gets connected to a line, okay, and that line is what you call your feeder. And it gets connected to that feeder, it goes to the transformer that you see, that's a 10 MVA, which is a 33 to an 11 kV, right? And that point, you then go into what we call your distributor, so that you have got those lines coming out that are 2.5 and the other one is a 3 MVA. So that's a radial. You're moving from your supply source directly to where your loads are, and your loads are those 2 MVA, the 2.5 and the 3 MVA at the end. And we usually say that for our radial distribution system, the system offers a poor security of supply to consumers, which is what we don't want. Remember, we said we wanted a reliable system. And why does it offer a poor supply of security? Because if you had, for example, look at between your bus bar 3 and your bus bar 2 on this diagram. If that bus bar had to be lost due to a fault that happened to it, or a fire, or there's a tree, it's an overhead line, and there's a tree that a farmer was cutting and it fell on that line and it breaks the conductors. It basically means that all those customers at the end, that load, which is 7.5 MVA, would be out of supply. So that's the reason that we say it's a very poor security of supply. It doesn't guarantee the customers any backup should something happen between your generation source to where they are. Then we go to your ring distribution schemes. At the bottom of the slide, we've got what is called a ring distribution system. And the ring scheme, really what it has is that from your source, which is the substation S in this case, going towards your far end load, which is O, you've got two feeders coming out. So one is going via the LFN route, and the other one is going via the SRQPO route. Now, if you had to have a fault where I just call that F on the upper part between your L and your M, you can obviously see that you're going to lose that portion then between your S and your M, which means that you can still feed the M load via the bottom feeder, which is the feeder going through from S to R, then through to Q, then to P, then to O, then to N, and it goes to your M load. So what it means is that irregardless of where you have a fault in this system, you are always going to have, as long as it's a single fault, you are always going to have an alternative route of going to where that load was being fed so that that load can remain in supply. And because of this, we say that this ring distribution scheme is a reliable system, and that's what we want for our distribution systems. And the last connection scheme we're going to discuss is what we call the interconnected scheme. And in reality, what you see in front of you is the ring distribution system that you saw on the previous slide. The difference is this red light that I've just put in there. And that red light, what it does is that it's called an interconnector. And what it does is that it links, that's why it's called an interconnector. It links the substation to the distributor that is on your far end. So it's a distributor or a load, it doesn't matter, but it links it to the one that is on your far end side. And by doing that, you're making your system more versatile, you're making your system to have less voltage drops in it, and the power losses that are going to be experienced are now going to be less between any of 2 points that you have in the system. And this system, we say it increases your reliability of supply even more than your normal ring, because whereas in your ring you had two alternatives, you have now introduced a third alternative to make sure that you are keeping the end station connected whatever is happening on your network. And therefore, any fault that's happening in there, you will still have continuity of supply being maintained. Thank you very much. That was the introduction of the chapter on distribution systems. So the next lesson is going to be talking about your direct current distribution, and then the last lesson for this is going to talk about our alternating current distribution.